Okay, today I think we're going to get into some crazy stuff. Some crazy stuff. Nah, that's not too bad. Today we're going to talk about two-way tables and independence. All right, independent two-way tables and some conditional probabilities. Okay, so beforehand, let's do a little review. My name is Mr. Krause. You can call me Mr. Key. Mr. Key. Hopefully I don't make too many mistakes. Don't forget, this is not a subscribe button, but it's a reminder to hit that subscribe button. I'd appreciate it if you do so. That would be fantastical. Let's get started. Justin would like to know the probability of getting an even number on the red die, followed by a prime number on the spinner. So this is going to be the probability of even. Because it is an and, we're going to multiply by the probability of prime. Probability of even would be, in this case, there are 8 of these things. It would be 4 out of 8. The probability of prime, 2 is prime, 3 is prime, 1 and 4 are not. So 2 out of 4 or 8 out of 32. Now, if you prefer, that's 1/4. I don't care. This one, more practice with prime, kids. This is going to be the probability of prime and the probability of prime. And means multiply, probability of prime. Now, why can I just multiply these probabilities? Because rolling the die has no effect on the spinning of the spinner. Rolling this die had no effect on how I spun the spinner. Rolling this blue die has no effect. It does not change the probability in the least. The probability of getting prime on the spinner, whether I roll the die or don't roll the die, has no effect. So I can just multiply those probabilities. The probability, let's see, prime, 2, 3, 4, no, 5, no, 6, 7, no, 8, no, 9, no, 10, 11, 13, no, 15, 17, and 19. So out of 20, there are 1, 2, 3, 4, 5, 6, 7, 8 prime numbers. And the prime numbers on this, 2, 3, 5, and 7. That would be 4 out of 8. 32 out of 160. If you prefer, I believe that's 1/5. Yes. All right, in a standard deck of cards, what is the probability of getting a full house, aces over kings? And for those of you that don't play cards, that means 3 aces and 2 kings. So the probability of getting, so this is really the probability of ace times the probability of ace times the probability of ace times the probability of king times the probability of king. Now, really what this is this is the probability of ace. This is the probability of ace already having got an ace. This is the probability of ace having already gotten 2 aces. This is the probability of getting a king having already gotten 3 aces, and so on and so forth. But we'll take care of that in the probabilities. The probability of ace is 4 out of 52. Now, the probability of getting an ace again is 3 out of 51. Now, this is the probability of getting an ace haven't already gotten an ace. So there's 3 aces left, 51 cards left. This is the probability of ace. There's 2 left out of 50 cards. This is the probability of an ace having gotten 2 aces, so on and so forth. Probability of king, 4 out of 49, and the probability of another king would be 3 out of 48. Grand total of, oh, I didn't write this down. I believe it's 288 over, where's my calculator? What if I have this big, ginormous number still in here? It's 311 million something. I don't. So 52 times 51 times 50 times 49 times 48, 311, 875, 311, 875, I think it was 200, or was it 250? 200. And if I reduce that, I'm just curious what this is. 288 divided by is 1. You have a 1 in 1,089,082,000 900 chance of that happening, of getting aces over kings. Woo! Not very likely, children. All right. What are the two tests for independence? We talked about those yesterday. And if you remember correctly, you can use probability of A is equal to the probability of A given B. That one or this one are the same. Probability of B equals the probability of B given A. That's one test. My other test is the probability of A and B is equal to the probability of A times the probability of B. Very simple tests to see if we're independent. All right, do you remember these two-way tables from yesterday? In fact, this is the exact two-way table we talked about yesterday. We talked about the marginal frequencies. We talked about the joint frequencies. Today, we're going to do a little bit different stuff. We're going to change things up slightly. Now, the probability of A we already talked about yesterday, scoring between 65 and 84. That was 99 out of 167. That wasn't too bad. The probability of B, what was B? Scoring above 85, that was 46 out of 167. The probability, now here's where we're going to change things up. Remember what this stands for. This is the probability of A given D has already occurred. In other words, as far as this goes, D is your universe. D is the only thing you can think about. It is the only thing you're allowed to even remotely think about is D. So let's go back up here. I have to ignore everything but D, and D is this. This is all I can think about, just this. This is my new universe. So given the fact that the only people I can talk about are the ones that scored or studied between 1 and 5 hours, how many of them were A as well? So given that it had to be between 1 and 5 hours, how many of them scored between 65 and 84? So I'll come over here, 65 and 84, 27. Now be careful. This is where this is going to get a little bit different. There are 27 that scored out of 48. I'm no longer using the total because I can only think about this row. So the answer is 27 out of 48. Let me do one more, and then I'm going to let you try. You should pause it then and try the next two on your own. So the next one says, what is the probability of D given that A has occurred? So A is my new universe. It is the only thing I am allowed to think about is A. The only thing I'm allowed to think about is A. What was this, 46, 48? So the only thing I'm allowed to think about is A. So let me go back up here, get rid of all my stuff. And the only thing I'm allowed to think about is A. I'm going to highlight A really, 65 to 84. This is my new universe. This doesn't exist. This doesn't exist. None of this exists. This is my new universe. Well, then what is the probability of D given A? Well, what's D? D is between, so this would be 27 out of total of 99. Now, while the numerator is the same, the denominator is not. Now, why is that true? Let's investigate that really quickly. This is the probability of A and D, remember the formula is equal to the probability of A times the probability of D given A, or the probability of A and D is equal to the probability of D times the probability of A given D. Well, remember what we're going to do in order to find this, because this is the thing we're looking for, is divide by the probability of A. So this is over the probability of A, which in this case was 48. Or the probability of, actually, I'm on the wrong one, probability of D, which was 99. I think 99. Probability of D was 48. But whatever, notice what the numerator is in each case. It's the same, which is why the numerators here are going to be the same. The denominators are going to be slightly different. All right, let's do the probability of B given F. So F is my new universe. The only thing I can think about is F. So let me figure out what F is. F is students that studied 6 or plus more. So this is all I can think about. This is my new universe. I can't think about you guys, and I can't think about you. This is the only thing I can think about. So this is the probability of B given F. Where's B? B is scored above an 85. So that's 31 out of 87. 31 out of 87. And finally, E given B. So B is my new universe, given that I have to stay within B. What's B again? Scored above 85. I'm given that I have to score in between 85. Given B, so this doesn't count anymore, and this doesn't count anymore. So what is the probability of E given B? Well, so basically what we're saying is how many of the kids that scored above 85 didn't study? 2 out of 46. All right, kids, that's that. Let's go. We're going to do some more, but we'll be right back. It was time for some coffee. Anyway, let's talk about this. Oh, man, I wrote this question, and all of a sudden Nintendo came out with that Switch. So whatever. Anyway, we got the Nintendo Wii, which used to be tops of the game, and then we got to Sony PlayStation and Xbox and so on and so forth. So you remember the two-way table, it's important that you add down. So in order, what I would do right now is try these on your own, just make sure you don't get them. But in order to save a little bit of time, I'm just going to do the work for you. This is 115. This is 654. And this is 231. And if I did that correctly, it should be 1,000. 333 here, 275, 283, 109. So there's my two-way table. Don't forget the stuff on the inside, all of this stuff in here are called the, what is this called? What do we call this, kids? Right? These are the joint. Remember the joints? Those are the ones that combine PlayStation with this or PlayStation with this. They're the joint frequencies. And all the stuff on the outside is called the marginal frequencies. Marginal frequencies. Just a heads up. So let's see what we got here. So probability of A favors Nintendo. 115 out of a grand total of a grand, 1,000. Probability 2. We're already starting into the joint probability, or the conditional probability. So remember, I'm giving you E. So E is you can only talk about 18 to 21-year-olds, or 14 to 21-year-olds. That's E. And I want to know how many of them, given that you have to be an E, how many of them are A? Oh, 35. So 35 out of 283. Because remember, my universe is 283. Notice how the denominator changed. Next one, probability of B. The probability of B favors PlayStation. 654 over a grand. This one, the probability of B given that we're going to be in F. What is F? 30 plus. Let's highlight F. F is 30 plus. So what is the probability of B favors PlayStation if I'm in F? Oh, 160 over 333. Probability of C. What is C? What is C? C is favors Xbox. 231 favor Xbox over 1,000,000. What is the probability of F given that we're in C? So my universe is C. C is my new universe. So what is the probability of F given that I am in C? Excuse me. What is the probability of, what number am I on? Given that I'm in C, oh, favors Xbox. That's C. Given that I'm in C, what is the probability of F? What is F? 14 to 21. So there's 12 out of the 231. Probability of, oh, now wait, this isn't conditional. This is an and. C and E. You got to be able to go back and forth, kids. C and E. This is where we're going to do this. C is favors Xbox. E is 14 to 21. Where is the and? Right there. 12 out of 1,000. This is not conditional probability. This is 12 out of 1,000. And finally, the probability of C given that we're in E. I want you to notice the difference between these two. Probability of C given that we're in E. Well, given that we're in E is 14 to 21. There's E. I can only talk about things that are here. So what is the probability of C given that we're in E? Probability of Xbox given that we're 14 to 21. Oh, that's 12 out of 283. Notice it's a much different probability when we do conditional probability. All right, kids, this one's a little bit different. Now we're going to change things up slightly again for you. So let's talk. Those that do not live in or near big cities may not realize that the majority of people actually do not actually drive to work. So if you live in a big city, you're probably not driving to work too much. The cost of having a car in a large city is very expensive. Because of this, many people choose to work or go to work or get to work via public transportation. The table below shows the data from 10,000 people collected that were surveyed. Now, I tried to make it easy for you because there's the table. I can answer questions about those tables, but you got to be comfortable not only seeing this frequency or joint frequency table, but you need to be comfortable with the relative frequency table. Now, a relative frequency table is a table that already displays the percentage of data in the frequency. In other words, it is already the probability. In many cases, it's already the probability. For example, probability, whatever. Let's erase that so I don't. Let's say I said, what is the probability of going by car and New York? Well, car in New York is this 500 people. 500 out of what? Oh, it's 500 out of 10,000. Well, I go to my calculator if I want to, and I go, okay, 500 divided by 10,000 And if I do control enter, because I want the decimal actually, 0.05. That's 5%. So 5% of people surveyed are from New York City and drive a car. So the probability of car and New York City is 5%. Well, in a relative frequency table, that's exactly what goes right here, 0.05. Now, let me tell you how we're going to get these. I'm going to do a few of them with you. This is 500 divided by the 10,000 total. This one would be 300 divided by 10,000 totals. I think you'll guess that that's 0.03. This is 1,300. Oops. Divided by 10,000. Or 0.13, or 13%. The total would be 2,100 divided by 10,000. Now you're going to see why I was nice to you. 0.21, or 21%. 21% of the people I surveyed went by car. Now the reason I said I was nice to you is because now all I got to do is know I got to move the decimal 4 decimal places. 0.13. 0.15, right? 1,500 over 800 over 10,000. 3,600 over 10,000, which would be just 0.3600. 1,100 over 0.11. This would be 0.07. 0.04. These are all frequencies. So basically what I'm doing is taking each one of these and dividing it by 10,000. To create the relative frequency table. 0.22. 22% of people take the bus. 0.09. 0.10. 0.02. 0.21. 21% of the people walk. Anybody want to guess what they have to add up to? Over here, this is 0.38. 38% of people lived in New York City that were surveyed. 35% of people lived in Boston that were surveyed, and 27% of people that were surveyed lived in Los Angeles. And if you add those up, they have to add up to 1. Because isn't that what 10,000 divided by 10,000 is 1? Now, why would I do this? Well, you just need to be careful. Sometimes you're going to be given a relative frequency table, which the probabilities, percentages, are already built in. Or you're going to be given a frequency distribution. So what is the probability a person picked at random would take a bus to work? Oops, given that they live in Boston. So this is the probability of bus given that they live in Boston. Now we got to be careful with this one. I probably started out a little bit tricky on you. So given that they live in Boston, so my universe is Boston. That's my universe. In other words, that's my denominator. My denominator is 0.35. How many take a bus that given? Oh, 0.07. So 0.07. So I go to my calculator and I do 0.07 divided by 0.35, and I should get 0.2, or 20%, 0.2. So given that they live in Boston, 20% of them will take a bus. What is the probability that a person picked at random lives in New York City given they take a bus to work? So again, now my new universe is taking a bus to work. There's my new universe. I don't care about this. I don't care about this. I don't care about this. My new universe is just here, bus. Now, given that I take a bus, now let me go back here. Let me write this out for you. It is the probability that they live in New York City given that they take a bus. So my new denominator is bus, and bus is 0.22. Now, what is the probability if I'm only in the bus column that I'm from New York City? And that would be 0.11. And I hope you all know 0.11 divided by 0.22 is just 50%. There is a 50% chance if you take a bus to work that you're from New York City. All right. All right, let's keep moving. What's the next one? Oh, is it more likely that a person in Los Angeles drives a car, or more likely that a person drives a car? Is it more likely that a person in Los Angeles drives a car, or more likely that a person drives a car that lives in Los Angeles? Oh my gosh, what is going on here? So here's what I'm asking. This is kind of a complicated question. Oops. So, probability, is it more likely that if I live in Los Angeles, I drive a car? So what's the probability of a car given that I live in Los Angeles? Or what's the probability that I live in Los Angeles given that I drive a car? Notice the two different probabilities. So this one is, what is the probability I drive a car given I live in Los Angeles? So given I live in Los Angeles is now my universe. It's the only thing I can think about. Live in Los Angeles. 0.27 is my denominator. What is the probability I drive a car given that I live in Los Angeles? Car would be 0.13. And if I did that on my calculator, I think I get 0.481. Now, car is my new universe. What is the probability that if I drive a car that I live in Los Angeles? So car is now my new universe. Here's my new universe. So now my denominator is 0.21. But so my car is my new universe. What is the probability that I live in Los Angeles if I drive a car? 0.13. And if I put that in my calculator, I get 0.619. So it is more likely that given they drive a car, they live in LA. That was a really pain in the neck question. That was there for fun. I hope you enjoyed it as much as I did. All right, so let's talk about this one. This is kind of what you're really going to be given. You're going to be giving a table with some holes in it, and you're going to have to fill in those holes. So this past weekend, I visited the Greater Rochester Auto Show. It's kind of cool, looking at all the cars I can't afford. And let's see what's going on. So here's the frequency table. I noticed that they were surveying the patrons as they left. The data they collected was below. So it looks like they were doing a little striation with males and females and car type, what their favorite car type was. So let's fill out let's fill out this top one first, and let's see if it makes sense. 337 minus. So I know that this total for Chevy has to be 337. I already have 110. So if I just subtract those, I should get 227. So 227 people liked males. Now 253 people liked the Fords, and I know that the females were 145. So if I took 253 minus, 145, I'll get 108. So 108 liked the Fords there. I already have these numbers, so the only thing I got left to do is fill out this number, which is 110 plus 145. Oh, come on. Every time this thing pops up, I wish it would never pop up. So 110 plus 145 plus, 143? Equals 398 every time. 398. Now I should check my work. I didn't even. Plus, what is it? 702. 1100. Now let me check the other one. The other one should work. 337. Should check it. Plus 253 plus 510 equals 1100. So 1100 people were surveyed. Now, if you look down here, it's not as easy as it was before. Notice it's not like this is 0.306. Well, where am I getting these numbers from? Well, don't forget, every one of these needs to get divided by 1100. So if I was to grab my calculator and do, what was that number? 337 divided by 1100, I should get, oops, and then hit Control Enter. I get 0.3063. And we'll round it to the tens place. So we're going to do 110 divided by that. Divided by, and I get, 0.1. That's an easy one, 0.10. And then we're going to take all of these, the ones that we need to, divide by 10,000, or by 1,100. 145 divided by 1,100. And we'll hit Control Enter. So 132.132. And, you know, I don't necessarily need to do this. I'll show you why. 367 divided by 1,100. And 0.334. Because if I add these up, they should be 464, right? If I add all these up, they should be this, right? And finally, this number over here, 702 divided by 1,100. And I get 638.638, and 0.638 plus 0.362. Remember, they got to all add up to 1. So I fill it out. So what is the probability that a patron chosen at random will choose a Ford given they are female? So it doesn't matter which one you choose to use. I can use either one of these. Well, I'll show you that I get the same answer. So given that I'm female, so that's my new universe. My new universe is given that I'm female. What is the probability that so this is the probability that I choose Ford given that I am, well, I should probably write Ford, given that I'm a female. So I can do it one of two ways. I can do, let's see, given that my new universe is 398, and given that I like Ford would be 145. If I use the other table, my new universe will be 0.362, and I like Ford to be 0.132. Now, whatever these are, they should come out to be the same. So 0.132 divided by 0.3362. 0.364. Now let's try the other one. 145 divided by 398. Notice I get the almost exact same results. A little bit off because of the rounding, but for the most part I'm getting 0.364. What is the probability a patron chosen at random will be male given they prefer Jeeps? So now I got to get rid of, now I prefer Jeeps. So what is the probability that a male, given that they prefer Jeeps or Chryslers? Well, Jeeps is now my new universe. My new universe is Jeeps. So what is the probability that if my new universe is Jeeps, that I am male? So this one would be 367 over 510. Or I can use 0.334 over 0.464. Either way, I'm going to end up at 0.72. So given that I like Jeeps, there's a real high probability I'm male. What is the probability that Peyton chosen at random is female if they prefer Chevy vehicles? So what is the probability of female given that they prefer Chevy vehicles? Chevy vehicles is my new universe, and I want female. So it's 0.10, 0.10 over 0.306. Or if I go to the other table, it's 110. Oh, I misread this. I totally misread this. What is the probability, and it's female and prefer Chevy vehicles. What is the probability I am female and prefer Chevy vehicles? Well, on this one, I can just read it. Prefer females and prefer, it's 0.10. Or that's my probability. In the other one, I got to go, oh, it's 110 over 1100. Either way, acceptable answer. All right. Is the fact that a patron chooses Ford independent of being female? In other words, is the probability of Ford equal to the probability of Ford given that they are female? Because that is going to prove independence. Is the probability of Ford equal to the probability of Ford given female? Well, let's see the probability of Ford, and the relative frequency table is easier to use. Its probability of Ford is right here, 0.230. So the probability of Ford is 0.230. Now we got to figure out what the probability of Ford is given that we're female. Maybe I'll come back up here. Well, it doesn't matter. You can use the same chart. What's the probability of Ford given that we're female? So let me get rid of all this stuff. Now, the thing is now, my new universe is female. So let me go get in my new universe. My new universe is female. So what is the probability of choosing Ford given that my new universe is female? So that would be 0.132 over 0.362. 0.132 over 0.362. Or in other words, 0.132 divided by 0.362, 0.364. So does 2.30 equal 0.364? No. So are they independent? No, they are not independent. Being Ford, or being female and liking Ford are not independent. And that was a very quick test for independence. All right, we done, kids. That's it. Tomorrow will be a full day of practice problems. Pretty tough. Some of them are going to be pretty tough. Some zingers in there. Let's see how you do. All right, kids, hit that subscribe button for me. Hit that like button. Tell me what you think. All right, catch you on the flip side. Goodbye.